Yeah, now it's being recorded. All right, so let me repeat. So we learn what is momentum. So Jyoti told me it is mass into velocity, correct? And then what is impulse? Impulse is if a force F acts on an object for a period of time t, the product force with the time through which it is acting is called the impulse, F into delta t. And we have this relationship between impulse and the change in the momentum. Okay. Impulse is simply equal to the change in the momentum. So there's a relationship between impulse and the momentum. It is like if a force acts on an object, it is going to change its momentum. Okay, so and the impulse is exactly equal to the change in the momentum. So it's kind of coming from the Newton's second law. It also has a name on its own called the impulse momentum theory. Okay, so we talked about, okay, it is fine for a constant force. What if in reality, the force is acting on an object is not going to be constant, like hitting a ball with a bat. It is going to start with a small value and come to a big value and die quickly. You know, it is going to act there for a short period of time, then it is going to die. So this is the nature of impulsive force. So, but however, we don't, we still have no problem. We will say impulse in that case is equal to some average value into the period, the duration within which the force is acting. So we choose this average force such that it is going to have the same area as the area under the actual curve of the force. So that is how we get the impulse even for a varying force. Okay, now we come to the new, okay? Those what I just went through, what we covered in the last class. Now we're going to discuss more into a system of object. So let's say we have a system, not just one single object, and the forces acting on this system will cause the center of mass of the system to accelerate as if the entire mass of the system was a point-like object located at the center of mass. Let me just make it clear. Let's say we have a system collection system, a collection of many objects, okay, M1, M2, M3. Then, its center of mass will be somewhere, let's say it's here, the center of mass. So when a net force acting on the system, so net force means there will be forces acting on, say, one of them, or force acting on different object, many forces. And we can say the net force on the system cause the center of mass to accelerate as if entire mass, see, so let's say M1, M2, M3, M4. So let's say the system consists of 4 masses. The net force will cause to accelerate. This center of mass will be accelerating as if all these M1 and M2 and M3 and M4 are concentrated at the center of mass. Then we can treat as we did for the 1 point. So we can forget about it is a system with a collection of masses. We can think everything is there at the center of mass, and the net force is acting on the center of mass, or a single object is now moving, accelerating. So we can again apply the Newton's second law by simplifying everything. So we will say the net force is all the forces. Net mean what? Everything, collection, you sum them. So there will be some forces which is coming from outside the system. So we will call this external forces. This is because the force from an object outside of the system. So we call it external forces. And there can be forces because of interaction between inside forces. Okay. So maybe, M1 will be exerting a force on M2. By hitting it or by attracting it or pushing it, electrostatic or electromagnetic or contact forces. But we know Newton's third law. Forces come in pairs. So if M1 is pushing M2 in one direction, M1 will be pushing if M1 is pushing M2 in one direction, M2 will be pushing M1 in the opposite direction. So these forces going to cancel when you sum them up. So only force that will come in will be the sum of the external forces. So we say it is equal to total mass, which is concentrated, as we imagine it is all concentrated in the center of mass point of the system, multiplied by the acceleration of the center of mass, because see, it is the center of mass is now accelerating. It's an imaginary point. It's not necessarily one of the masses. It is the center of mass. We have to apply the formula and get the center of mass position. So that particular point is going to accelerate. So we have now the equation, Newton's second law, applied to a system, a collection of the object. So this is the equation now. So far, we've been applying the Newton's second law for just a single object, treating it as a point mass. Now we can also do this even for a collection of objects. The trick is to find the center of mass of the collection of the object. And we will say the net force acting on the system is equal to mass of the total mass of the system multiplied by acceleration of the center of mass. Okay. Right. So now we have very important principle, conservation. You know what is conservation mean, right? Meaning it doesn't change, it remains the same with time. So that is what conservation, it remains constant. So this is nice because this momentum quantity, which is the mass into velocity. So if it is a collection, mass into velocity of the center of mass, the total momentum, which is going to be the total momentum has or we can apply a law called conservation of linear momentum, total linear momentum, for a system, provided it is not always true. If the external force is zero, if the net external force is zero, then we know previously we had this equation. External force is equal to mass into acceleration of the center of mass. So we can also write, okay, external is equal to total momentum, the rate of change of total momentum. If this is zero, that means the rate of change of total momentum is equal to zero. If something does, what do you mean by the rate of change of total momentum? The momentum does not change if it is zero. The momentum does not change with time. If something has a time rate is equal to zero, that means it is not changing with time, right? If the velocity does not change with time, then delta V divided by delta T is equal to zero. That means velocity remains constant. Similarly, if the momentum, total momentum, does not change with time. Suppose we have this equal to zero. It is true if the net external force is equal to zero, then the total momentum of the system will remain constant with time. So that is the law of conservation of linear momentum. Is it true all the time? No. When is it true? When it has no external forces acting on it, or maybe there are external forces, but somehow they cancel each other. So the net external force is equal to zero. Then we can say with confidence that the total momentum of the system will remain constant. It doesn't mean the individual momentum is not changing. Okay, maybe we have a collection of things, say M1 and M2 object. So say this has P1 momentum, this has P2 momentum. P1 will change, P2 will change, but P1 plus P2 will not change. All I am saying is the total momentum will remain constant, provided there is no external forces acting on this system, okay? Well, how? You know, it is because of the Newton's second law. We are proving mathematically. Yeah, because see, we got this equation, right? If this is zero, mean this is zero. What is the meaning of delta P over delta T equal to zero? meaning P does not change with time. So if you ask me how, I can only say that is what you observe, because from observation only we get the Newton's second law. Okay, by doing, then we confirm our law by doing experiment, which is, this law is confirmed, verified again and again. Okay, so that's why it has become a law. Conservation of linear momentum is a law that applied very widely, of course, but under condition. What is the condition? There is no net external forces acting on the system. Okay, right. Now we have got a question. An ice skater standing on ice is tossing a water bottle in a vertical direction. Consider the skater and the bottle as a system. Is the momentum of the system conserved? Ignore friction. So let me draw the picture for this. And he has a water bottle and he throws the water bottle up. So when he throws it up vertically, we consider system. Okay, you have to define what your system is. System is the water bottle and the skater. This is our system. The system consists of this skater and the water bottle. Now he throws it up. Okay, let's say he throws it up, vertically up. Now, when he does that, the question is the momentum of the system conserved? What do you think? What is the condition for it to conserve? Our system is water bottle and the skater, right? The condition is zero net external force. So let's look at the forces on this system. There are forces, right? mg. Okay, but mg is balanced by the normal force. What about the bottle? Bottle has its own weight. So let me call it big mg. So this is small mg. And on the water bottle, as it throws, there will be a normal force on the water bottle. So it looks like, in the first sight, everything, if he is not throwing actually, if he's just holding it without throwing it up, all the forces are balanced. So the net force on this system is 0. But the moment when he throws it up, what happens is he needs to apply an additional force on the bottle to make it go up. Because if N and mg are balanced, will the bottle go up? No, it will be in equilibrium. So he has to push this up with a certain force that will make, even he will be pressing hard on the ground, that will make the force acting on the person also to increase more than the weight. And you cannot make the bottle go up without increasing the normal force on the bottle greater than, so let me call this NB and this is MM. The NB has to be greater than mg for the bottle to go up. So on the system, we are going to be a net force. On the system, there will be a net force. If there is net force, can the total momentum be conserved? No, there is a condition. Total momentum is concerned only if there is no net force. Okay. Right. So let me look at the solution. These are the choices we have. You have to pick the correct choice. Yes, because the momentum of any system always is wrong, right? We have a condition. What is the condition? The net force should be, net external force has to be 0. Okay. Well, here you will argue, okay, these two are, mg is external force to the system, and this mg is also external force for the system. So, but you say if he is stationary, is not trying to throw it up, the external forces are balanced, okay? But when he, external force, what are the external force? The N from the hand on the bottle, and there will be a force of N on the hand. These are internal forces. External forces will be these two and this also. From the floor on the man will be an external force. So as he tried to throw up, eventually the normal force from the floor on the man will be greater than the weight of the man. So there will be external force the moment he tries to throw up. So our answer is A is wrong, because he says always. That is not true anyway. It is only true when the net external force is 0. B, yes, because the net external force is equal to 0. That is also wrong. Okay. C, no, because the net external force is not 0. Yeah. And we have to explain why it is not 0, because when you start throwing it, the vertical forces are not balanced. Okay, the normal force is going to be greater than the mg. This is wrong answer. You cannot say never conserved. It is conserved under certain circumstances. No, because the external force is not 0, and the answer is explained there. What I was telling you right now. There is a question from Abdullah. How can you determine what are the external forces? Very good question. Okay, how can you? Now here, let me draw the picture. You define your system, right, Abdullah? You define your system is the man or the skater plus bottle. Any force between bottle and the skater is internal, because bottle is part of the system, the man is part of the system. So any force between the bottle and the skater is internal. If there is a force that is coming from outside, acting on either the skater or the bottle, it is external. So the weight of the bottle is external. The weight of the skater is external, because where is it coming from? From the earth. The earth is not part of our system. So our system is just the skater and the bottle. Okay, and the normal force from the ground on the person, also on the skater, is also external, because we defined our system. We defined our systems to be the bottle plus the skater. Are you satisfied with the answer? What about the friction? Yeah, friction is from the flow, right? Not from the between bottle and the skater. That is also external. Friction is also external. But anyway, in the question, he says ignore friction. So that is why we didn't even discuss that. Abdullah? Okay. If you didn't ignore it, even before, without the friction, the answer is there are external forces. Even if the friction is not there, okay, there is external forces which is not balanced when he tried to throw it up. Okay, so it doesn't matter. Okay, whether we ignore or not, it is the same answer. Other than the friction, there are other external forces, and that external forces are not going to be balanced when the persons try to throw it up. Okay, okay, right. So we have another question to clear up more. Now it's the same question, but same scenario, but here he is throwing the bottle in a horizontal direction. If even for the previous question, the momentum is not conserved along the vertical direction, but in the horizontal direction, it is conserved. We can apply the conservation of momentum in each direction separately. So suppose the net force is equal to 0 in the horizontal direction for some reason, then momentum is conserved in the horizontal direction. It may not be conserved along the y direction, because it is the net force is not 0 along the y direction. When he throws it up, the momentum is not conserved in the y direction. We saw that. But if there is no friction, okay, if there is no friction, this is the second question. Let me discuss the second question. Now this time, okay, it doesn't matter which direction he's throwing. It can be even throwing vertically upward. Consider the skater and the bottle as a system. Is the momentum of the system is conserved in the horizontal direction, ignoring friction. So in the horizontal direction, even though he is only he's throwing it in the horizontal direction, okay, he is throwing the bottle in the horizontal direction, okay. Now, in the horizontal direction, all the forces are internal. because we are ignoring the friction. The only external force in the horizontal direction, if it is there, it is the friction force that coming from the flow and the man, the skater. But we are ignoring the friction. So once we ignore the friction, there is no net force in the horizontal direction. So the momentum is going to be conserved in the horizontal direction. Well, it is going to be conserved in the vertical direction as well, because you are not throwing it up vertically, you are throwing up horizontally only. Therefore, even in the vertical direction, the net force is 0 when he throws only horizontally. And also in the horizontal direction, anyway, it is 0. So the total momentum of the system is conserved in all directions. In horizontal direction, it's anyway conserved. So the answer is yes, because the momentum, that is not the correct explanation, okay? Yes, the net force is equal to 0 in the horizontal direction. That's why it is conserved. No, because of the momentum. The explanations are not correct. Question? What about air resistance? Yeah. Yes. We totally ignore the air resistance, okay? So air resistance is completely ignored because actually it is very small, okay? So it is ignored. Yes, because that is right. So now we have a question to answer. What is the question of the answer again, please? What is the question of that answer? The second part of the question, okay? The question is this. Consider the skater and the bottle as a system. Is the momentum of the system conserved in the horizontal direction? That's the question, okay? And the answer is yes, because the net external force is equal to 0 in the horizontal direction. Okay, is that fine? Okay, right. So we have a question now. I mean, numerical question, okay? That was concept statement question. Now this time we have to substitute and get the answer, numbers. An ice skater of mass 45 kilogram, initially standing on ice, tosses a 1.2 kilogram bottle at a speed of 14 meters per second at an angle of 34 degrees with respect to the ground. The skater recoil on the ice. If friction is ignored, what will be the recoil velocity of the skater? So let me go to the question. So there is a figure. Now this time, she's not throwing it up or throwing it horizontal. He's throwing it at an angle. So we have the velocity in both x direction as well as the y direction. Okay. In the y direction, it is not going to be conserved anyway. It will be only conserved in the x direction. So we can say the total momentum in the total momentum before x direction. Total momentum in the x direction before is equal to total momentum in the x direction after. So I'm using two subscript here, okay? Total momentum in the x direction only, before and after has to be the same. What do you mean by before? Before is before she throws the bottle. After mean after she throws the bottle, when the bottle left her hand. So we will say before total momentum in the x direction is equal to before total momentum, after total momentum in the x direction. Is that clear? So we are applying the conservation of momentum in the x direction, because in the x direction, the net force is equal to 0 because we are ignoring the friction. All the other forces are internal forces because he's pushing the bottle, and the contact forces from the bottle on the hand and from the hand on the bottle, these are all internal forces. And only horizontal force that can come is due to the friction. We ignore the air resistance, okay? We ignore it is actually very small. We can ignore it. Friction, it can be have an value, but we are saying, okay, it is perfect ice, there is no friction. Now, we apply the equation which says momentum, total momentum before is equal to total momentum after is just a statement of conservation of momentum. Total momentum, okay? Not the momentum of any one individually. Total momentum, the collection of all the momentum, but only in the x direction. Okay? Because in the y direction, it's not going to be conserved because they're going to have a greater normal force on the foot, on the skater than the weight, okay? So there'll be net force in the vertical direction. Right, so what is this? Before she throws, she's at rest. The bottle has a 0 velocity. The skater is also 0 velocity. So that means before she throws, the total momentum is 0 plus 0. 0 for the bottle and 0 for the skater. What is 0 plus 0 equal to? 0. That is before. Afterward, let me say it is this total momentum afterward. So 0 afterward, the bottle mass, what is the definition of momentum? Mass into velocity. But I only want in the x direction. So the mass of the bottle, velocity of bottle in the x direction afterward, plus mass of the skater multiplied by velocity of the skater in the x direction. S for skater, x for x component. Okay, right. So we got this equation. Now, mass of the bottle is given, mass of the skater is given. Velocity of the bottle is given. Okay, she says it throws with a certain speed at a certain angle. So it is given. Only thing we don't know, what happens when she throws the bottle, you know, right? If you're in an ice skating ring, and if you throw something, you will move backward, recoil, it's called the recoil. Okay, so that is what we are doing here. So we are saying total momentum before is 0 because the bottle has 0 velocity and the skater has 0 velocity in the x direction. Okay, any direction before, but anyway, in the x direction is what we are interested in. Afterward, they will have velocity. So we will say the total momentum because therefore they will have momentum. So now do you understand how we get from this to this algebra? Can I skip that part? It's okay. You want me to show it? Okay. All right. So here, 0 is equal to MB VBX plus MS VSX. Okay. Now I'm going to take it to this side, one to the other side. Is it okay? It's okay, right? Now, then I'm going to take the minus MS to down. So MB VBX divided by MS with a minus sign. Very good. Now you substitute. Now what about substitution? Let me clear everything. MB is 1.2 kilogram. Fine, this is good. VBX, let me go back to the question. It says it is thrown with a speed of 14 meters per second at an angle of 34 degrees. Let me go to this. So this velocity of the bottle is, what did I say? 14 meters per second. And it is making an angle of 34 degrees. This means VBX is equal to 14 cosine 34 and VBY is equal to 14 sine 34. Is that right? No, your x component will be velocity multiplied by the cosine of the angle that velocity makes with the x-axis. V14 cosine 34. Y component of the velocity will be velocity multiplied by sine of the angle that makes it the x-axis. So that is why we have here 14 multiplied by cosine 34. That is the x component of the bottle's velocity after it is thrown. Divide by mass of the skater. There it is. You get a negative value. So because we have chosen the direction of the bottle's velocity as the positive direction, so we are getting a negative answer. So you should understand that means the skater is moving backward in the opposite direction to the bottle's velocity. shouldn't the velocity be different? I didn't understand your question. Different from what? Which velocity is different from what velocity? Oh, you got it. Okay. All right. I didn't really understand the question. Anyway, never mind. She got it. Perfectly inelastic collision. Right. Now, we're talking about collision, okay? Now, we said momentum is conserved only if the net external force acting on something is 0. When we have collision, like a car collision in an accident, these are collision. You know what is collision mean, right? Hitting each other, two things, two objects. So in a collision, we say the total momentum is conserved. I mean, then you might ask, okay, is the condition satisfied? What is the condition? Net force? No. Well, let me look at that, okay? We say it is conserved. And you probably asking, how can you say with certainty? What about the external force? So let's say two things collide in the air. Two things collide in the air, okay? Well, in the flow, maybe two cars colliding. In the horizontal direction, the momentum is going to be conserved because if we assume there is no friction, okay, if there is no friction. But even if there is friction, we can say something about this collision. If I look at the momentum of this car, let's say this is P1 and the momentum of this car is P2, just before collision, okay, just before collision. Then after collision, this become P1 dash and this will become P2 dash. So can I say P1 plus P2 vector, okay, P1 plus P2 is equal to P1 dash plus P2. That means is the momentum conserved, total momentum? I'm sorry? Yeah. We have to do it properly, okay? If something is negative, you have to put negative. But I'm not assuming any direction. Suppose both of them are moving in the same direction, both of them positive, right? And then after colliding, one guy will be going like this, other guy, we don't know, okay? We are not assuming, we don't worry about it. What I'm asking is, for this to be true, the net external force has to be 0. But it's strictly not correct because there will be friction and so on, okay? But the point is, what I'm saying is just before the collision, let's say the total momentum is P1 plus P2. Just after the collision, say the total momentum is P1 dash plus P2 dash. I'm going to say they are going to be equal. Because let me tell you, there is friction, there may be external forces, but this collision occurring for a very short period of time, like millisecond, collision, okay? So I am only watching this. We are looking at the momentum just before collision, just after collision. We are talking about fraction of a second, millisecond or microsecond. So if I only interested in the total momentum right before and right after, there are external forces. Yes, there are external forces. But those external forces are nothing compared to the internal forces that are going to happen when they collide. When they collide, the forces are huge, right? They will be hitting each other with great force on each other. It may be like 10,000 Newton or whatever. But the external, those external forces like friction and all will be going to be small compared to this. Additionally, this collision is occurring for a short period of time. Okay, short period of time. So we can ignore these external forces as long as you are only talking about the total momentum right before and right after. We can safely say the momentum, total momentum is conserved. Okay, now, just forget about whatever I said. We just remember in a collision, as long as we are talking about the total momentum right before and right after, the total momentum is conserved. That's it. Okay, period. Is it fine, guys, online? So you should understand what I said now. In a collision, the total momentum is conserved. But we are only talking about the total momentum right before and right after, not later on or not long before. Very good. So we're going to I have a question. Abdul Hussein. Okay. Right. So we have a question now, a collision problem. Two masses M1 and M2, they are moving in the same direction. So one-dimensional collision. Okay, we'll stick to one-dimensional collision only, because if it becomes two-dimensional, they have to apply in the x direction, y direction. So in the x direction, horizontally only. And M1 has a velocity V1I. So, is a mass number 1, so velocity number 1. I for initial, before collision. So this is the velocity of M1 before collision, I for initial. And M2 has a velocity, so let me call V2I, but we make it 0 because we want to take a simple case, okay? So when one of them is 0, the equation becomes simple. Then also we make it even simpler by saying after collision, they join together. Okay, after collision, they become glued together, entangled, stick together. So that means there is only one velocity after collision, right? Because M1 and M2 are one now. Both of them have the same velocity. So we are only talking about just one velocity. Let me call it VF. There is no need to call it V1F and V2F. There is only one speed after collision, right? So we are going to apply the conservation of momentum for this collision. Can you tell me what is the equation I should write? Momentum before is equal to momentum after. I can write it like this: Pi sigma is equal to Pf sigma. Let's bring it again. All right, so this is a question. If I know M1 and M2 and V1I and V2I, the masses and the initial velocity, can I find the final velocity of the system because they stick together? Is it possible to do it? Applying what? Conservation of momentum. You will say total momentum before is equal to total momentum after. By applying that equation, we can determine the final velocity. We'll see how. Okay, this is the velocity of the first object. It has an x velocity and y velocity is 0. Okay, well, never mind that. Okay, we will just apply this equation. What is this? Well, let us do it without looking at the solution. Okay, so we will say the momentum before is equal to momentum after in the x direction, of course. So M1 multiplied by V1I will be the velocity of momentum of M1. What is the momentum of M2? M2 multiplied by V2I. So this is the total momentum before it collides. Equals after. What is the total momentum? There is a no. We don't. This is what. This is the picture. This M1, M2 is become one mass and it has one velocity. So the momentum after will be the mass, total mass multiplied by its velocity, which is, we don't know what it is. Let us label it Vf. So we know this. We know this. And we know this not as a number. And we also know this as 0 because the question says M2 is at rest. It's in the question. M1 has a velocity, is moving. M2 is at rest. It's given in the question, okay, for this particular problem. Afterward, they become just one object and has a velocity Vf. So this is the total momentum before, and this is the total momentum after. And we say they are equal. That is conservation of momentum. So I can write that equation here. Then from that, I can come to this. You want to see how? You bring it to this side. So it will be M1 V1I divided by M1 plus M2 is equal to Vf. It's very easy, right? You just bring it to this side so we get this equation. What is this? So this is, if you know the masses, and if you know the initial velocity of the incoming object, initial velocity of the stationary object is 0, so V2I is not even there. So we got this nice equation, which can give us the final velocity, provided we are given the masses and we know the initial velocity of the incoming ball object. So there are more questions in that. What do you observe when M1 is much greater than M2? Let's look at the equation.
Doctor, may I ask a question?
Sure.
What if the V initial for the second mass is there? It's not equal to 0.
Not 0, you mean?
Yeah.
If the second mass is also moving, then the equation will become, so we'll have, this will be there, right? So Vf will be M1 V1I plus M2 V2I divided by M1 plus M2. So it will not be that equation. Okay?
Okay. Thank
you.
You
know, because we want to take the simple case here. Yeah. So let's discuss this question. He's asking, what if there is another what if? What do you observe if M1 is greater than? See, M1 is much, much greater than M2. Pen is here. Suppose this M1 is, let's say, 1,000 kilogram, and M2 is only 1 kilogram. It's like we have the M1 is a big ball, and M2, which is at rest, is a small ball. And this big ball and coming and hit, you know, without even physics, you can kind of answer this.
I think in this case, the final velocity for M2 will be different from M1.
They stick together. So they have to have the same velocity. The question says, after collision, they stick together. So we have to agree on what the question says. The question says they stick somehow. The both ball, after colliding, they stick together. Now, about the final speed, if M1 is greater than M2, this pen is driving me crazy. Okay, if M1 is very much greater than M2, what happens is, they can say this is almost equal to, you can ignore the M2. It is like it is not even there. So M1 will cancel with M1. You will get the final velocity will be almost the same as the initial velocity of the incoming ball. Because the small guy, which is blocking him, the small guy is blocking him, it will not change its velocity at all. He will just stick to it. Suppose the guy came with the velocity of, say, 10 meters per second, and he is stopped. After collision, he will almost going with the same 9.99 meters per second with the small guy. You can understand that. Even without physics, you can make sense of that, right? But the physics tells you it is the case. Okay, right. So here he's showing it. Yeah, he mean in the limit when it M1 or much greater than M2, the ratio VF over V1I is 1. That means VF is almost equal to V1I because the ratio is 1. Yeah. You can ignore this limit part. Okay, just you say if this can be ignored, that means M1 divided by M1, so that is 1. VI is the same thing, in terms of limit. Yeah, I think we have reached the end. I think I will let you go. Yeah, it is almost time. Okay, thank you. Is Abdullah Jaman?
Doctor.
Yeah. Yes.
For the last part, when M2 has a bigger mass than M1, in this case, it's just going to stop the whole.
Yeah, very good. We can do it as an exercise. What if the small guy who is sitting there is big? M2 is big, and what will happen is, if they stick together, the whole thing will come to zero velocity. Yeah. And you can prove it using the equation also. It will be nice if we can check it. Yeah, very good. Yeah. Okay. Thank you. So I will stop now. See you in the next class.
Thank you, Doctor. Have a good day.
You too. Thank you, Abdullah.